here is our units for temperature and pressure. So Kelvin is going to always be our unit for temperature. Do you remember why it's so important that we convert to Kelvin? Yeah, do you going to remember why that is? Number one, it's universal, right? That's the thing that's the most important. But second of all, our equations won't work if we have a 0 in the denominator, right? If we have 0 degrees Celsius, we can't do calculations if we're dividing by 0 degrees Celsius, right? We can't make that happen. So mathematically, our temperature value has to be greater than 0. And so by converting to Kelvin, we have that option. 0 Kelvin would be absolute 0. So that would be like Dunzo. Pressure conversions. These are ones you might need to write down. I'm okay if those go on your equation sheet. Do you remember these pressure conversions, getting from something to atmospheres? Right, atmospheres. Do you remember what this one is called? Millimeters of mercury. This one's kilopascals, torr, and then PSI. What's PSI stand for? Pounds per square inch. Pounds per square inch. We usually see this one in what? What do you see PSI in? Inflation. Yep, like tire pressure, things like that. So I'm okay if those pressure conversions go on your equation sheet. I wouldn't really necessarily expect you to have those memorized. It's equals, not minus. This device right here is called a barometer. Have you heard of that term before? Barometers measure atmospheric pressure. That's the whole point of a barometer, is to measure atmospheric pressure. Sometimes they hang like in a column on the wall. Sometimes you'll see it on a wall barometer. So it's like a piece of wood and it's got a column of mercury right there in the middle. That's exactly what happens. There's a little reservoir of mercury at the bottom. Okay, and then you have a column of mercury that goes up the top. And so the height of that column, literally in millimeters of mercury, is the atmospheric pressure at that time. So it says mercury flows out of the tube until the pressure of the column of mercury standing on the surface of the mercury in the dish is equal to the pressure of the air. So you're looking at basically the column and the dish of mercury to be equal pressures. That way it's not flowing one way or out. And then that will tell you what the atmospheric pressure is at that point. So standard atmospheric pressure, what we feel typically in our everyday world at sea level, right, is going to be around 760. I don't have a barometer in here to know what daily atmospheric pressure is, but you'll see like when storms come through or something like that, you could check the atmospheric pressure and see what it is. Okay, so we know the pressure units and the temperature units, but here is our actual values. Most often we use 273 and 1 atmosphere. Okay, those are the two actual temperature and pressure values that we use the most, because we like our pressure to be in atmospheres and we like our temperature to be in Kelvin. So these are the two values that we use the most. Kilopascals is like the second most common pressure unit, and it's used pretty often, but for the most part, we want them to be in atmospheres. Okay, and we'll kind of talk about when it's important to have the units in a certain, or to have the certain particular units, and sometimes it's okay as long as they're the same on both sides. All right, so we're going to start with Boyle's law. Okay, Boyle's law. Do you remember what the equation is for Boyle's law? Bingo. P1V1 equals P2V2. You boil something at a constant temperature, you leave temperature out, right? So this is talking about the pressure and volume relationship. Okay, P1V1 equals P2V2. They are inversely related. I wanted to say indirectly, which is the same thing. Inversely related, so that means when one goes up, the other goes down. Okay, this one should go on your equation sheet. For problems like this, our units are not such a big deal as long as they are consistent on both sides. So if this pressure was kilopascals, this pressure would need to be kilopascals. As this one was milliliters, this one would have to be milliliters. So you can keep them the same as long as they are consistent on both sides of your equation. That's really the only thing here. When we get into a couple of different equations, we'll have to make changes regardless, but for right now, those ones are okay. So let's go ahead and try one here. 1 liter of gas at STP is compressed to 473 mils. What is the final pressure? Okay, grab your calculator out if you don't have it out just yet. 1 liter of gas at STP is compressed to 473. So I'm going to start making my list here, right? My V1 equals 1 liter. T1 equals 273 Kelvin. P1 equals 1 atmosphere. It says, what is my final pressure? So P2 is my question mark. And V2 would be what? Yeah, but what does it need to be measured in? Yeah, 0.473 liters. Now, I think you guys are probably to the place where you can do this without making the list. Fine with me, right? It doesn't matter to me if you feel like you can go ahead and just plug it right into the equation. That's perfectly fine. Okay, so P1 times V1 equals P2 times V2. And so that gives me a value of 2.11 atmospheres, right? And since my original pressure was in atmospheres, my final pressure is going to be in atmospheres as well.
So do we even need to put the temperature?
No. Nope. Mm-mm. Nope, we don't have to include temperature. If I have 5.6 liters in the gas in a piston at a pressure of 1.5 atmospheres and compress the gas until it's a volume of 4.8 liters, what's the final pressure inside the piston? Do you know what a piston is?
Yes.
Right? It's just like a movable cap basically on a container, right? So it's going to move it up and down and be able to change the volume of that container. Okay. So this would be V1, P1, V2, P2 is my question mark. Charles' law is looking at the relationship between volume and temperature. They are directly related, which means when one goes up, the other goes up. So here's our equation for volume and temperature, or Charles' law. V1 over T1 equals V2 over T2. All right. So let's look at an example here. This is one where we talked about it's really important for us to convert our temperature to Kelvin, because we cannot have a temperature in our equation here that's 0, right? I cannot have a denominator equal to 0. So our temperature does have to be converted to Kelvin every single time. All right. I have 67 liters of helium in a balloon at 28 degrees Celsius. So 67 liters over. And do you remember how to convert from Celsius to Kelvin? Yep. Plus 273. So that gives me 301 Kelvin. It says I'll increase the temperature of the balloon to 47. So 47 plus 273 is 320 Kelvin. I'm looking for V2. And then mathematically, how am I solving that one? It's just a cross multiply and divide, right? Just cross multiply and divide. So 320 times 67 divided by 301. Nope. Okay, let's try it again. All right, how about 71? Yep, 71.23, and our unit's going to be liters. Okay, because our original volume unit was liters. All right. Why don't you try this next one here on your own? Try this one on your own.
We always went to a whole number in Calvin.
No, you can keep 1. I just thought it was close enough to a whole number. I went ahead and rounded. You could put your answer back into Celsius if you wanted to, but it's one of those things that unless I tell you specifically, I'd probably accept either one, right? You just don't have to convert it back to Celsius. If you wanted to, you would just subtract out 273. But unless I tell you specifically, I don't think you need to convert that back. This is another relationship that we didn't really look at last year, but it's a relationship between the number of moles and the volume of an object. And this is really how Avogadro's number kind of came about, right? It's all this relationship between between the number of moles of a gas and the temperature of a gas. And it all kind of came about here, but he developed this relationship, or this understanding the relationship between the moles and the volume of a particular gas. It works as long as our temperature and our pressure stay constant. Okay, so N is always our representative of moles. N is representative of moles, and V is your volume. Okay, so let's just try a practice one with this. Okay, if 2.45 moles of argon occupies a volume of 89 liters, what volume will 2.10 mole of argon occupy under the same conditions? So all I'm going to do is go 2.45 moles over 89 liters equals 2.10 moles over V2. Okay, so again, we're really just examining this kind of ratio or relationship between the two. And so at that particular amount, or that quantity, 2.10 moles, we would have a volume of 76.3 liters. Okay, so this one's really kind of just looking at a relationship. We're just taking quantity of that gas away, which would therefore take away volume, right? If pressure and temperature stay the same, that's what we would look at. All right. Last real gas law here we're going to look at is Guy-Lussac's, and that's the last relationship that we haven't examined, and it's one between pressure and temperature. They are also directly related, which means if one goes up, the other one will go up. And so it's P1 over T1 equals P2 over T2. Right? It looks just like Charles' law, okay, except we're using... Charles' law. Yeah, okay. I thought I said it wrong, but we're using pressure instead of volume. Okay. So let's look at the example listed here. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 to 30 degrees Celsius. So P1 is 1 atmosphere. 20 plus 273 gives me 293. P2 is what I'm solving for, and that means our final temp would be 303. Would we expect our pressure to rise here or fall? Rise, right? So my pressure final is 1.03 atmospheres. right? These are directly related, which means if one goes up, the other goes up. Think about that, right? If our temperature increases, we are moving faster, right? Our particles are moving faster. They have more energy. That means they will collide with the walls of the container more often, which that's what pressure is, right? Is how often or how much force is being applied over a certain area. Okay, that's where we put all of them together. Disregarding Avogadro's law, right? We're not with moles yet, but the combined gas law puts together all three. So in all reality, this is the only one you need to know, right? Because you can break the other three out of this one. Okay, that's why it's called the combined, right? We're putting all three together. So really, all you need to know is this one. And then if there's no pressure involved, you just leave pressure off. And if there's no volume involved, you leave volume off, right? But it's those three gas laws put together into one called the combined. So again, even in the combined gas law, our pressure units, as long as they are consistent, can stay. Volume units, as long as they are consistent, can stay. But temperature always has to be in Kelvin. Always, always. Okay, that's the only one that for right now has to be changed. All right, let's try one here. A balloon has a volume of 1.8 liters. The temp was 20 degrees Celsius and pressure was 1 atmosphere. If the balloon rose 3 kilometers into the sky where the pressure is 0.66, does it matter to us that it rose 3 kilometers into the sky? No, it does not. Okay, that number should not throw us off anywhere, right? Tells us the final pressure and the final temperature. We're looking for V2. That's going to be my question mark. All right, so P1 times V1, so that's P1. All right, P1 V1 over T1, let's see, 293 equals 0.667 times V2 over 263. Okay, so let's do our math to solve for V2. All right, mathematically, I just did cross multiply, divide, and I'm bringing that one down too, right? I cross multiplied and divide by 293, divide by 0.667. Simple enough? All right. I'm going to go ahead and stop